Good afternoon.
Good afternoon, Doctor.
We continue. We continue application of water process integration methodologies in all refineries and petrochemical complex. It's a case study. Mhm. The slide is available in Elite, including the papers. I will revise the slide slightly and share with you the revision in a new paper as well. Bismillahirrahmanirrahim. The application of water process integration methodology is in oil refineries and petrochemical complex. So this slide is based on Handbook of Process Integration, chapter 21.3, and paper by Muhammad Hassan, the bottlenecking procedure of effluent thermal treatment system, and Panjay Shahi, optimum design of cooling water system for energy and water conservation. And last is cooling water system design by Robin and Jean. Okay. Process plant typically comprise several interconnected process units and central utility system. The process integration technique provide a rational framework to identify opportunities for energy and material conservation and efficient use of water of use source in process industry. This is the why we do process integration. And water is used for a wide variety of purpose in the chemical and petroleum industry. In the past, water had been assumed to be a limitless and low-cost commodity, but increase in water awareness, scarcity of this resource, and increasing in water costs have encouraged efficient water system design. So we conduct process integration for water as well. Before this, it's for heat and energy. Water and wastewater mineralization in a refinery. You can refer to handbook of process integration. I think I show it in the ELIP, page 669. The an oil refinery plant includes several water consuming operation. The main component of the water and wastewater system include the water network and the cooling tower. It's important, cooling tower. The existing performance parameters of the base case for the water network site and the cooling cycle site cooling tower are presented in table 21.17. So, wait. So before I forgot, for final exam, for my part, you need to study last week presentation, especially on how to construct water pitch, especially limiting composite curve, LCC. You can refer to what is this book? Chapter 10, but inside the slide, yeah, there's a method how to construct it. And another question is about what is it? Grand composite curve. Utility selection. Grand composite curve. Last week presentation. That one will be in final exam. And another one is problem table algorithm. So three things you need to learn for final exam for my part. The others I'm not sure. So continue. The existing performance parameter of the base case for the water network site and the cooling cycle site cooling tower are presented in table 2117. So for water network site, you have several performance parameter for cooling cycle site. Yeah, you have several. This is the existing before the integration, process integration. Project objective. In this project, a new strategy is implemented for the minimization of water and wastewater in a petroleum refinery complex. The implemented solution strategy can minimize the water requirement by using an advanced water pinch method. So advanced water pinch method here refer to the traditional method using in combination with the software. In this case, they use MATLAB. So water pinch. Taking advantage of the most recent technologies for improving the quality of recycling water and increasing the water reuse rate. The proposed solution strategy set performance target prior to design. Consider This is targeting. Start to do the process integration now. Consider a water using operation in a refinery process. In order to minimize the water consumption and to maximize the material use, from other operation to this operation, first the water with the highest inlet concentration should be specified. Then by specifying the maximum possible outlet concentration, the water will be minimized at the maximum inlet concentration. So table 2132, sorry, figure 2132. Let me see. Yeah, that one. This profile, the limiting water profile, is a representation of a limiting case that will not necessarily be used in the final design. Therefore, any water supply line below the limiting profile will meet the requirement of process and operational feasibility. Then table 2118 present the limiting process water data in water and wastewater system of the refinery. Table 2118. So the pinch letter will based on the table 2118. So we have 9 stream here. The first step is targeting the minimum water flow rate by constructing the LCC, limiting composite curve. So how to construct this refer to the previous session. As shown in figure, the inlet and outlet concentration of the process define the concentration interval. So how to know the inlet outlet from the process or PFD, process flow diagram, or anything that have that data. The limiting composite curve is obtained by combining operation within the concentration interval. Okay. The second step is to define the feasible cooling water supply line from composite curve and the parallel supply line. Refer to figure 2134. Oh no, okay. So once you've done the limiting composite curve, then you can draw line to determine the pinch. Okay. Step 2 is the second step is to define the feasible cooling water supply line from the composite curve and the parallel supply line. So here is the actual pinch here. Then okay. Then determine the feasible region. The feasible region is the this is the feasible region. It's based on the paper by Muhammad Hassan. Yeah, Muhammad Hassan. Can refer it in ellipse. Then the next step is to target the third step is target the cooling water supply condition from the cooling system model and the feasible cooling water supply line. Detail of the targeting procedure are given by that paper that I mentioned, Muhammad Hassan. Six B. So figures 2134 they is actually the line AB represent the attainable condition from the cooling tower model by changing the configuration from centralized to distributed arrangement. It has noted that the inlet condition to the cooling tower affect the cooling performance. So at the x-axis is the flow rate. At the highest flow rate, the C out is minimum. Then they plot the variation from highest to the lowest and see how the trend for the concentration. Yeah, concentration. Not sure why concentration. It should be temperature. Wait, wait. Should be temperature. Okay, okay. So in the original paper, the C here is actually T. But because in table 2118, beside the temperature, the other variable is changing as well. Sorry, 2118. The suspended solid oil, COD, and so on. So they base it based on this other material. Then the design stage. In this stage, the objective is to design a water network for targeted condition, flow rate, and concentration using pinch migration. We learn this later through temperature shifting concept and Waterman method. Following the Waterman method, often allow more than one network design to achieve the target. In the design of the water system, certain design features are essential. So to calculate the new pinch temperature, we can use this. I will show how to use it later. It is necessary for the cooling water to be reused in the design to achieve the target. The design procedure is then followed with strategies to further decrease of external freshwater requirement to reduce the operational cost of the water and wastewater system. Water transfer. So increasing the cycle of concentration in cooling system provide the opportunity to reduce fresh makeup water by improving the quality of the recycling water in control tower. That one is the first design, increasing the cycle concentration in the cooling system. The second one is integration of the ozone water treatment with cooling system for to improve the energy efficiency of cooling cycle. So first one we introduce increase in cycle of concentration. Then that water you need to treat it using ozone because it is safe, non-chemical and eco-friendly. So the incorporation of ozone will remove the biofilm that accumulate on the cooling system component that impending impeding the heat transfer. Yeah. So pinch migration. So in paper by cooling water system design by Robin and Jean, refer to section 3.2. Design of cooling water network without a pinch. Water system water system focus on the minimization of contaminated water to the environment, which forces the design of water network to the minimum consumption of water. The cooling water supply line should be based on consideration of the overall system. The cooling water system cannot operate beyond a specific return cooling water temperature because the hot return cooling water temperature might cause falling problem, means scaling, yeah, corrosion, or problem with the cooling tower packing. It is common practice to introduce temperature constraint for returning cooling water to the tower. So for cooling water network, the system has a number of components that and there are interaction between different parts of the system. So minimum flow rate, if there could okay, minimum flow rate of cooling water is not necessarily the optimum. The cooling water supply line should be based on the concentration of the overall system. So if the cooling water supply line does not correspond with the minimum flow rate, either because of the system saturation or the temperature constraint, because of the third point here, the setting could be between minimum flow rate. Oh, the setting could be between minimum flow rate, maximum reuse, and no reuse parallel arrangement as shown in figure 10. Figure 10. So this is the Waterman method is based on the concept of the pinch point and cannot be applied to problem without pinch. So this is for maximum reuse, no reuse, temperature limitation. The limiting profile represent the boundary. Sorry. So the new cooling water supply line is here. If the temperature is high, we turn back to the third point. So we cannot use this pinch and need to introduce a new cooling water supply line. The setting could be bit okay. So the limiting profile between the boundary between feasible and infeasible operation. In other words, any composite curve with below the original one is feasible. Thus, the cooling water composite curve can be modified in the feasible region without creating feasibility problem. So, hang on, bye. So within this maximum reuse and no reuse is the feasible region. If the cooling water composite curve could be modified to make a pinch point with the desired cooling water supply in the feasible region, the cooling water network problem would be changed into a problem with a pinch. So we still need a pinch, but because the new cooling water supply line is not near the composite curve, so we need the pinch migration. Pinch migration is introduced here to convert problem without a pinch into those with a pinch with the desired supply line. So there's a two method to do pinch on here. See the visible line of. So we need to shift the composite curve to reach the new cooling water supply line. Two approach to pinch migration. So the first approach is either first is to shift the heat load. The first sorry, this the number one heat load shift. So shift the heat load in which the cooling water composite curve move along the heat load axis or the x-axis. The second approach is to shift it based on the y-axis of the temperature axis. Of the two approaches, temperature shift is adopted because heat load shift will result in energy penalty. See here, it's more than the previous Q. So meaning you need for energy penalty, you need either you need to use more fuel to provide the energy to cater for this energy. Then we choose a temperature shift, but how to choose? But how to choose? Find the new pitch, pinch, and modify the composite curve. So you introduce a new target temperature of 55 degrees C. For the cooling water, a new pitch is created between the modified composite curve and the new supply line, which is calculated from the simple heat balance figure. The new calculated pinch of 38.5 degrees C is migrated from the original 40 degrees C pinch. So the original pinch point is at 40, then shift about 1.5 to 38.5 here. So you will have a new composite curve. It is necessary to for individual duties to apply a temperature shift for modification of the composite curve. Cooling water, stream 1, 2, and 3 take part in creating the original pinch, which means stream 1, 2, and 3 are the candidate for temperature shift. The limiting cooling water modification are in two stages. The first stage is to shift the temperature of the limiting water profile according to value of the temperature shift 1.5 degrees C for this example. The modified profile might cross the supply line and thus another step is needed. The second stage is to increase the flow rate of the limiting water profile when the shifted profile is restricted by the temperature limitation. The limiting cooling water profile is modified to satisfy temperature limitation by increasing the cooling water flow rate. Okay. Proposed strategy for design. This is incorporating ozone in water treatment for cooling system. So the first proposed strategy is sorry. The first proposed strategy is to increase the cycle to reduce the fresh makeup water. Then that water need to be treated using ozone. The purpose is to remove the biofilm accumulated on the side of the cooling system component that reduce the heat transfer. Finding. Following the targeting procedure on the case study, petroleum refinery complex, the result of targeting stages are presented in 2119. So the freshwater consumption now is 77. Before this is unlimited. The wastewater evaporate flow rate is 50 millimeters. So 8 per meter in total. The specification of the water network at pinch point are represented in table 2120. So pinch point for this case study is at 30 degrees C. Suspended solid is 4 ppm and so on. It was attempted. Yeah. It was attempted in the design stage to achieve design feature that met the targeted value. Having applied the design procedure, table 2121 show a comparison between the performance target at the targeting and final design stage. So at design stages, there's a discrepancy. for air cooler heat transfer area and water ozone treatment capacity. So water ozone treatment capacity is the new unit operation. If you were to if we were to increase the cycle, water and energy saving. Figure 21.36 show the final modified configuration of the water wastewater system. Applying the proposed solution strategy resulted in 31.3% freshwater conservation and 93.9 kilowatt energy saving in the water and wastewater system of the refinery plant. Table 21.22 shows the economical evaluation achieved from the solution strategy. So the payback period time is 3.3 years. Another case study is effluent treatment and regeneration. Refer to Handbook of uh, Process Integration, 21.4. Mm. Okay. Oh, okay. Refer to Handbook of Process Integration, page 693. Debottlenecking of an effluent thermal treatment system in a petrochemical plant. And paper by Muhammad Hassan, yeah, similar debottlenecking procedure of effluent treatment, thermal treatment plant. Introduction. Treatment of wastewater is required to solve effluent contamination problem to meet operational and environmental criteria. The assessment of effluent quality include issues related to concentration of pollutant, In the effluent stream, chemical properties of effluent, discharge flow rate, and temperature of the effluent. For solving issues of effluent thermal treatment, the introduction of the cooling system is therefore necessary to effluent temperature reduction. So basically, before we can discharge the effluent, the temperature need to be reduced. So we need a cooling tower. Debottlenecking of effluent. Okay. While while chemical, physical, and while chemical, physical, medical treatment process can be used for controlling the chemical pollution problem of effluent, a thermal treatment system is required for effluent temperature reduction problem where the temperature of the effluent stream is too high to be discharged directly into the receiving water. A typical effluent system in a petrochemical plant incorporate wastewater producing processes and a cooling system which interact with each other through water and energy flow. So consider some of the possible changes to an existing effluent system. For example, a new wastewater stream might be introduced into an existing problem. This is just a case study how it's happened. Or the heat duty of the wastewater stream change or process change might change the operating condition. These process changes influence the thermal treatment performance and consequently affect the condition of the discharge stream into the environment. In such situation, to overcome the this is the case study to overcome the bottleneck effluent cooling system. A combined water energy analysis procedure is required. The proposed solution, a new effluent collection point is introduced into the existing effluent cooling system, which bottleneck the thermal treatment process. Table 21.38 shows some of the ECP data. So the new one is ECP4, flow rate 58.33, temperature around 48 degrees C. The environmental temperature discharge limit is 30. The operating performance condition of the effluent cooling system with the new ECP are given in table 21.39. System with 3 ECP, the previous system. The inlet water temperature is 44.2 with inlet water flow rate is 277. With the new ECP CP4, so 44.7, the inlet water flow rate is 336. The percentage changes for inlet water temperature is 1.1, then inlet water flow rate is 20.9. The heat load is 26.3%. As shown in this 21.39, the discharge effluent temperature is hotter than desired environmental temperature limit, which is 30 degrees C. This means additional cooling equipment needs to be installed to cool the effluent to meet the environmental criteria. Then the heat load of the treatment network 20.8 watt is bigger than the heat removal of the tower 16.47. which also means 4.33 megawatt of the heat load need to be dissipated by additional cooling. So figure 21.54, the best case of effluent thermal treatment network, shows the, okay, so project objective. In this project, a methodology solution strategy for overcoming the bottleneck in the effluent cooling system of a petrochemical plant is implemented. An attempt is made to solve the problem through feasibility analysis of the cooling system with respect to the effluent network while keeping the cost of the bottlenecking as low as possible. For targeting, the proposed procedure is outlined in figure 21.55. So the targeting procedure applied to this project is carried out in three main steps. Construct the composite curve, of course. Then to define the feasible region and identify effluent supply. The organization design stage is final design, pinch migration and grouping rule. Right. Step 1, construction of the effluent composite curve. To construct the effluent composite curve, the disposable heat to be removed by cooling for each effluent stream is first calculated. The heat load requirement of each individual stream is graphically represented on a plot of temperature versus disposable heat 21.56a. The composite curve is constructed by combining all individual profiles into a single curve within temperature interval, figure 5b. Step 2 is to define feasible region taking into consideration the evaporation loss effect and modify the composite curve through temperature shifting. The feasible region is bounded by the maximum flow rate B and minimum flow rate A of the effluent supply to the cooling tower. Mm. The heat removal of cooling system increases as the configuration changes from fully centralized to maximum distributed. In figure 21.57b, the second figure, the line AB represents the attainable condition from the cooling tower model by changing the effluent network configuration from centralized to distributed arrangement. Okay. Though the cooling water supply line has the same heat load from the withdrawn of the effluent network, but the heat removal of the cooling system is changed as inlet connection to the cooling tower are changed. The heat removal of cooling system increases. So the effluent composite curve, this is, this is the feasible region. The oh. So the feasible cooling water supply line can move from C to D. The target condition which specify the desired discharge temperature are found by changing the cooling water supply condition from C to D. So targeting the cooling water supply, cooling tower supply, the feasible cooling water supply line can move from C to D. Okay. Then the heat removal of the cooling system is the same as the heat load of the effluent stream entering the tower where the discharge limit temperature of effluent network is satisfied. The target connection achieved from the intersection between the feasible supply water supply line and the cooling tower supply line. So here the target condition is 52.2 degrees C and 993.75 kilogram per second. Mm. The aim of the design stage of the proposed solution is to modify the existing configuration of the effluent system through the pinch migration concept, applying the design grouping rule. Uh, Pinch migration meaning temperature shift. The grouping rule is based on the concept of pinch technology and cannot be applied to problem without pinch. It has been noted that any cooling water line at or below the composite curve profile is considered to be a feasible design. So either we shift it based on heat load or temperature. So as shown in 21.59, because the new water supply line create no pinch with the effluent composite curve. So the target new supply line is due to temperature and the effluent composite curve should be modified to make a pinch point with the targeted water supply line within the feasible region. So the debottlenecking of cooling water system. When cooling water network need to increase the heat load of individual cooler or new heat exchanger is introduced into an existing system, cooling water system can be bottleneck in this case, as the increase of cooling load influence the cooling tower performance, and there are interaction between cooling water network and the cooling tower. The best solution is often obtained by modifying the cooling water network. So design procedure for debottlenecking of cooling water system. Yeah, first is composite curve. From the you must construct the composite curve using the limiting cooling water data. The cooling water network performance can be changed within a feasible region that is bounded by the maximum reuse and the parallel design supply line. The cooling water supply line has the same heat load, 20.8 megawatt. From the viewpoint of the cooling water network, but the heat removal of the cooling water system is changed as inlet condition to the cooling tower are changed. Okay. In figure 21.57b, the heat removal of the cooling water system increases as the design configuration changes from parallel to maximum reuse. A to B in A to B. For this example, the following condition should be satisfied for the new cooling water network design. So the heat removal from the cooling water system should be equal to the heat load of the cooling water network. The next stage is to find the target supply condition. This is how to find the target supply condition. For the cooling tower, the feasible cooling water supply line can move from maximum reuse to parallel design, no reuse. Uh, A to B, the target condition which specify the desired temperature to cooling water network are found by changing the cooling water supply condition from C to D. The heat removal of the cooling system is the same as the heat load of the cooling water network at the target condition. Okay. Pinch point to modify the composite curve. Pinch migration is applied on the basis of temperature shifting. The new pinch point can be calculated through equation 21.3. The new pinch point is calculated as 43.03 degrees C. The feasibility constraint on the target supply temperature are expressed as T water in is in between T min for T water in, T min, and T water in for the maximum T water in. And for T water out is from minimum to maximum temperature for T water out. The feasibility constraint on the target supply flow rate is as minimum water in is between mass water in is between minimum and maximum water in. So finding tutup dah. Okay. Having the aforementioned targeting step, the feasible new water supply to cooling system is achieved table 21.4. The final design of the debottleneck effluent cooling system is mentioned in the figure 21.61. So 21.4, table 21. Table 21.41. So feasible water supply is T in 52.2 degree C. The T out is 26. So mass flow rate is 193.75 with Q is 20.8. So 142.35 kilogram per second is not going to the picking the cooling tower and straight to the effluent. So the effluent is 32 at 30 degrees C. Table 21.41 shows the economic comparison between the implemented solution strategy and the best case. It was revealed that if the centralized design were adopted for the thermal treatment, best case, the additional cooling cost, including both capital and operational costs, would be 21.24 k $1,000 per year, while the proposed design strategy require additional pipe with their associated piping costs. For splitting the effluent stream, this result in 61% cost reduction compared to the best case. So for cooling water system design, the bottlenecking heat dot distribution for the bottlenecking the proposed so another point I didn't put it in the slide. Another point to note for cooling water system design is the heat load distribution for debottlenecking. The proposed debottlenecking procedure for cooling water system maintain high temperature and based on the paper by Robin and Jean. The proposed bottlenecking procedure for cooling water system maintain high temperature and low flow rate of return cooling water to increase the heat removal capacity of the cooling tower. However, the increase in temperature is not favorable from the viewpoint of water treatment. Higher temperature increase the corrosion potential in cooling system. The corrosion rate increases with increase in temperature and corrosion rate doubles for every 10 degrees C rise in temperature. Also, falling is related to temperature. For For example, calcium carbonate, which is the most common scaling problem in cooling water system, has inverse solubility characteristic with temperature. So the temperature limit for return cooling water are required when cooling water treatment is important. Also, if plastic packing is used in cooling tower, it should be able to take the required increase in temperature without deforming or degradation. This will cause a deterioration of cooling tower performance in the next. Okay. Okay. Think that's all for the case study. But inside the handbook of process integration, there's a lot more case study that you can view. Yeah, beside petrochemical, but I choose petrochemical and water for this case study. So, do you have question? There's a lot method for water pinch. I need more time to cover all. I'm given just a whole week. But for the final exam, yeah, do not the advice in the beginning of this session. So I think so those who haven't taken their attendance can do it now. And can refer to the paper. So thank you. The video will be posted in Elip, the recorded session.
Betul.
So next week, sorry, I think Mr. Farid will continue with let me check. With industrial application and case study, water recovery or flue gas recovery. So thank you.
Thank you, sir.
Thank you, Doctor.
Thank you, Doctor.
Okay.
Thank you,
Thank you,
doctor.
Doctor.